Okay, so we arrived to the maybe boring part of the lecture where we would formally show how to define an NFA. But first, a reminder about power sets. So given a set, the power set usually written as P of Q, but it's usually to write it as 2 to the power of the set, is all the set of all subsets that you get of the set, right? So if you have a set of 4 elements in this case, right, the power set is going to have 16 sets. And all those 16 sets for this example are listed here. So this is the power set. And let's continue for NFAs. So NFAs like DFAs are, well, NFA again stands for non-deterministic finite automata. And again, it's defined by a 5-tuple. So we have the states, Q, we have the alphabet, we have the transition function, which is going to be more painful in this case. We have the start states and we have the accept states. So from the main difference from our point of view is that the transition function now is going to be significantly more complicated. Okay, so let's look in the transition function. So the transition function is now going to be a function from a state, the current state, and the alphabet. In fact, here it's missing a parenthesis, right? Because it's and now it's a state and an input character or an epsilon, right? Because we can have epsilon transition. And the important thing is that now, because we might have multiple options, the transition might go from this state into a subset of states. So instead of the transition being into a state like in DFA, now we are moving into the power set of the states, right? So from every state and every input character, the NFA might move to a set of states that it might be in after handling this input. Okay. Okay, and importantly, as I just said, the transition function is a set of state instead of just being a single set. So let's go through this formal definition for this automata. The set of states here is just a list of the states. The alphabet is 0, 1. The transition function we'll do shortly because it's going to be a mess. And the rest is pretty standard, right? Okay, so let's do the transition function, right? So let's look on Q epsilon, right? We're in Q epsilon. And first, now we need to write the transition function for every character in the input and for epsilon, right? So if we insert Q epsilon, we get epsilon. First, we might always stay in the state we are in. So in this case, it's just going to be Q epsilon. Notice that this is true for every state, right? The transition from a state with an epsilon always is going to include the state itself. Okay. Q epsilon with 0, well, we might stay where we are, or we might go here. So this is the set Q epsilon Q0, right? We might be in those two states. Let's do the next one. Q epsilon 1, well, the only option is to stay where we are by taking the self loop. So this is for that. Okay, now let's do the Q00. Okay, so Q00 on epsilon is stay where you are. Q00 on 0, well, there is no transition, then the state of states that you might be in is empty, right? And Q00 on 1 is, of course, to go to QP. Okay, so this is that. Okay, next one. Q0. Q0, on epsilon, we might either go to Q00 or stay where we are. So this is Q0 or Q00. Q0 on 0 can just go to Q00. And Q0 on 1 is an empty set. Okay? And the last one is QP. which is of course is easy because on any input it just stays where it is. And that's it. Okay, so writing the transition function for NFA is quite messier and requires much more care because the transition function is more complicated, but the rest is very similar to DFA. And this is it for now.